Hello there. In this video, I'm going to go over the method that I use to calculate the zeros of a quadratic that is factorable, but when the lead coefficient is something other than 1. And what inspired this video was a comment from a viewer that asked a question that I'd actually never really thought about before, and I really delved deep into it, and I felt like at the end I needed to share my findings, okay? The link to the original video was a short, so it shouldn't take you long. I'll leave it in the description. You can go ahead and watch that first for some more context. But at the same time, I'm going to start from the original problem of that video. It was f of x equals 8x squared minus 2x minus 1. And instead of actually finding the zeros, I'm going to go ahead and factor this. Okay, so the method was I'm going to start by taking 8 and I'm going to multiply it by 1. I'm a big champion of the method of using diamond math to factor quadratics. But diamond math only works when your lead coefficient is 1. So I'm effectively taking that 8 and I'm moving it with the 1. So instead I'll call it big f of x. I don't want to call it the same thing because it is now a different quadratic. I get x squared minus 2x minus 8. Now see, the question was effectively, why don't we also multiply by -2? Which is a good question because we're working with what looks to be something like distribution, but we're only giving it to one number instead of 2. And so that's the question I hope to aim and understand. So the method first. So now that I've multiplied 8 by -1, I can go ahead and set up my diamond math. Okay. So I put my -8 up top and my -2. Now really quickly, we can think through the factors of 8. That'd be 1 and 8 and 2 and 4. Now, they need to multiply to give me -8, so one of them needs to be negative and one needs to be positive. Well, the fact that the 2, or the -2 I should say, is the sum means that the larger values would need to take on the negative sign. So I'll write the negative in there. And now we can add these up. 1 plus -8 certainly does not give me -2. 2 plus -4 does. So I put 2 here, -4 here. This is just a visual representation. It's no more different than if you just didn't write this at all and just worked through it out in your head. But I've often find as an educator, giving the students something to look at, some kind of process to work through rather than just say, well, just figure out two numbers that are multiplied in -8 and add to get -2, goes over a lot better because it keeps their pencils moving and keeps their brains working. Okay, so now I'm working with f of x, big F of x equals x plus 2 and x minus 4. And so when I was solving for zeros, what I initially did was I set these equal to 0 and I'd solve, and then I'd have to divide by the 8 again. So since I'm not solving for 0, I have to do that now. Okay, so 2 over 8. That's 1/4. So I would rewrite this as x plus 1 over 4. And then 4 over 8 is x minus 1/2. The reason why I'm doing this is because this factorization of x plus 2, x minus 4 is not the factorization of the original function, but the factorization of the modified quadratic. Now, this right here is also not the factorization of the new one, nor the old one. So what I do is effectively move this 4 out in front. What I'm doing mathematically is multiplying just this factor by 4, which would move the factor out front. So I can write it as little f of x now is 4x, and then 4 times 1/4 would just cancel and give me the 1. Same idea here. I'm moving the 2 out in front. I get 2x minus 1. And if you were to set both of these equal to 0 and solve using the zero product property, you would find you get the same solutions that I did in that short. So here's reason one why we don't multiply by the -2. When we multiply the 8 and the -1, we need to undo that at some point. So working with the constant allows us to, at the end, only have to divide by the constant instead of having to worry about how will this affect the linear term. Now I know what you're thinking. That sounds like a very bad reason, and you're right. That is not the greatest reason in the world. In fact, it's not even a robust reason why we should do this. So let's look at an abstract viewing of the problem. Okay, so in this abstract viewing of the problem, I've written out a polynomial, specifically a quadratic, with some weird looking coefficients. Now, to some of you, the answer may jump off the page at you. For others, it may not, and that's why we go through this method. We got to think, what multiplies to give me BD, but adds to give me AD plus BC? We have to remember AB, C, and D are just integers. You could work this method if you had rational coefficients. You can't really work it if you have irrational coefficients. But to keep things simple, I'm just working with integers. And so AD plus BC, this thing right here, will be an integer. Okay? So this is where the method would come in. Let's go ahead and take AC and multiply by BD. And again, I'll rewrite it as capital G of X, so we know we've got a different polynomial. X squared plus AD plus BC X plus, and I'm going to rearrange it. A times C times B times D. I'm going to go ahead and rearrange this, and you'll see why I'm going to rearrange it. Remember, multiplication is commutative, so I'm going to go ahead and do A, D, B, C. And it may be clear to you why I did that. You don't have to do it. The answer still works out to be the same, but it's nicer this way. So I'll go ahead and set up my diamond math. AD, BC, and then I have AD plus BC, okay? Now, what two numbers multiply to give me AD, BC, and add to give me AD plus BC? And that would be AD and BC. Remember, A and D, while being their own separate integers, A times D would be a whole new integer. So we can write this as G of X equals X plus AD, X plus AD times X plus BC. But I have to undo that multiplication of AC, so I'm going to divide AC here. I'm going to divide AC here. And notice we have some things we can remove. So I can remove the A's here, and I can remove the C's here. Now this will effectively allow me to kick the A out in front here and the C out in front here. So I get now my factorization of the original problem, G of X equals CX plus D times AX plus B. So to show you this works in a general form, I still haven't shown you that it technically works, because I could just be making this stuff up and working through the problem and saying ta-da, and really pulling the wool over your eyes. So let's go ahead and multiply and FOIL this out. So I'm going to use my area model. So AX and B, CX and D. And so let's go ahead and do this really quickly. A times C is AC, X times X is X squared, B times C is BC, and then we get the X. We get A times D is AD, and we get X, and then B times D is BD. And when we're going ahead and putting this back together, we get AC X squared. We add these two together, and I'm going to factor out the X to just make it look nicer. AD plus BC X plus BD, and we get the same thing that we had in the beginning. So this method works in a general sense. Now, that doesn't really explain why we don't also multiply by the middle term. Let's think back to what the original question was. Now, I could show you this by showing you the method in full and trying it out. So let's go ahead and do that. Let's go ahead and look at G of X equals AC X squared plus AD plus BC quantity X plus BD. So let's try this problem again. Let's go ahead and multiply by both. Let's distribute. So I get x squared plus, we get a squared cd plus a times b times c squared. So a, b, c squared x, and then we get plus. And I'll rearrange it in the same way I did before. Okay, so this would allow us to set up our diamond math. We get a, d, b, c in the top. We get a squared cd plus a, b, c squared. We can already see it doesn't work out to be the same. If I take out an AD here, we'd still be left with AC. And if I take out a BC here, I'd still be left with AC. So there's an extra factor rolling around that doesn't allow us to work. But let's go ahead and take a look at this through another window, and that's using the discriminant. Okay, so looking at through this at the discriminant, I've written down the general form of the quadratic formula at the top. The discriminant is b squared minus 4ac. The general rules and how this is taught in schools is if the discriminant, being the part under the square root, is greater than 0, then there exists two real solutions. This being because we have a positive number underneath a square root, which is a real number. The whole sum and difference would be real. If it's equal to 0, well, the square root of 0 is 0. What effectively would happen is that the square root would go away and you get negative b over 2a, which is just one solution. The two real solutions would be taken care of by the plus or minus, but that goes away with the 0. And then if it's less than 0, then there exists 0 real solutions or two complex solutions, depending on where you're at in your education and what your teacher wants you to know. The hidden agenda here, and the thing that I never really learned until I became a teacher and worked it out for myself, is if our discriminant is equal to a perfect square, and again, we're keeping in mind that a, b, and c are integers, although they probably could be rational numbers at the same time. The point is they're not irrational. And if you want, I can show you an example of that. But if the discriminant is equal to a perfect square, then there exist two rational solutions. Now, why is this the important one we need to focus on? Because if it's a perfect square, then it has rational solutions. This means it can be factored through the diamond math method. Okay? If it doesn't have rational solutions, that means we've got a square root or pi or e or something weird floating around somewhere that's an irrational number that's preventing us from factoring this polynomial the way we want. So let's go ahead and look at our original quadratic, 8x squared minus 2x minus 1. Let's go ahead and just find the discriminant of this alone. So a is equal to 8, b is equal to negative 2, and c is equal to negative 1. So b squared would be negative 2 squared, and I'll write it up here, b squared minus 4ac to remind us what the discriminant formula is. Okay? Minus 4 times a is 8 times c is negative 1. So here we get a negative 2 squared, that's 4. Now, I write a minus, but I also notice that we have a negative here. Negative times a negative would give us a plus, so let's take care of that right away. Then we get 4 times 8 is 32, plus 1 is 30, or times 1, pardon me, is 32, and then we get 36. 36 is a perfect square. It is 6 times 6, okay? So this confirms that this has rational solutions and therefore is factorable through the diamond math method. Now, let's go ahead and multiply and go work with our big F of x equals x squared minus 2x minus 8. Okay? Let's go ahead and we got a is equal to 1, b is equal to negative 2, and c is equal to negative 8. And we'll set it up. Negative 2 squared minus 4 times a is 1 times c is negative 8. Now, could we go through and work this out? Sure, absolutely. It wouldn't take us long. But I'm going to rather point out that we start with the -2 squared in both instances. So far it's the same. We've got the minus, got the minus. The 4 is constant and is always there, so of course we have that, as was the minus. Now here's where it differs slightly. We have 8 times -1 and 1 times -8. Well, 8 times -1 is -8. But also 1 times -8 is -8. We have effectively, and not strictly, used the commutative property to switch the 8 and the 1 where we kept the negative where it was at. So this again will give us 4 plus 32, which is 36. By multiplying to our constant term 1, we have not changed the discriminant because we've just effectively not 100% done this, but flipped A and C within the discriminant formula. But that's okay because multiplication is commutative. Now let's take a look at that if we had done it both. So if we have multiplied by here as well, we get x squared minus 16x minus 8, and then we can work it out. So negative 16 squared minus 4 times a is 1 times -8. Now here we would get the plus 32. But now that we've changed our b value, we get a whole extra factor of 8 effectively being counted twice. So negative 16 squared would be 256, and now it is 288. So we've changed the polynomial enough to the point where not only will we not get the same solutions, we won't even be able to factor this anymore. Now, obviously, these two right here, while they have the same discriminant, they'll get different solutions, but they're both indicative of these polynomials are factorable. 288, it's very close to a perfect square. In fact, I believe it's one off from a perfect square, but it's not a perfect square. So while we'll get two real solutions, we no longer get a factorable polynomial, which is why we don't multiply. Really quickly, one last thing I want to do in this video is I want to prove this in an abstract sense. So let's go ahead and go back to our abstract quadratic, and let's go ahead and note, now we kind of need to keep in mind that a from the discriminant is different from a here. Maybe I should have used different letters. I hope you will forgive me. But it'll ultimately, so the b value, the linear term will be ad plus bc squared minus 4. The lead coefficient, the original a value would be ac, and then times the constant, which would be bd. So really quickly, this is the big part we have to work out. So ad, bc, ad, bc. We get a squared, d squared. We get a, d, b, c, a, d, b, c, and we get b squared, c squared. So we're going to come out with a squared, d squared, plus 2 of these, 2ad, bc, plus b squared, c squared, minus this, which I'll rewrite as 4adbc, because now it matches this. But we have 2 of these, and we're subtracting 4 of these, so we'll write a squared d squared minus 2adbc plus b squared c squared. Okay, that's a mouthful. Where did this take us? This took us from a perfect square minus something to a different perfect square. Notice this a squared d squared minus such and such is the same as what I have here, but with a minus instead of a plus. So this right here is also a perfect square, and if you work it out, it comes out to AD minus BC squared. And now we have the perfect square we wanted to show that this is factorable and has rational solutions. Okay? If we go ahead and multiply, and really quickly, I'm going to fast forward through this so I don't take up any more time than I need to, we get AC plus B squared minus 4 times 1 times AC B, A squared B squared plus 2A DBC minus 4ABBC. Oh, no. B squared equals minus 4ABBC, and A squared B squared minus 2ABBC plus B squared with A minus BC squared. Now, I would go through and do this again. I was actually thinking about it, and I had planned on it by multiplying this and this to show you that it doesn't work out. But then I remembered the number one rule of rigorous proofs is if you can prove it on a general sense, then it's always true. Whereas if you can find one example where it's not true, then it's a general falsity. So here is my general proof that we only want to multiply by the constant and the constant only. Here is my counterexample of why you don't want to do it to the linear and constant term. I know this was a very long roundabout way of answering the question, but I felt like it was worth diving into the findings and why we do the things we do when we do this method. This is not a method that I find is very popular. Variations of it are popular, and I can understand why. People find what they're most comfortable with. And this is a method I've cultivated. I wouldn't say I invented it, but I've cultivated different aspects of different methods into this method over the years. And it's been what I found the students I teach understand the most, which is why I put it in my videos. If you have any thoughts, comments, questions, please leave them in the comments section down below. Otherwise, like and subscribe would be really helpful. And please keep those questions coming. I absolutely love them. Thanks for watching.